I decided after listening to Nima that I will try to make a talk without using the word infinity. And I will try to discuss about fundamental constant, and just to tell you why I was interested in these things about, let's say, 14 or 15 years ago, that there were a paper saying that some constants were varying. I mean, some people have detected that some constants were varying in time. And of course, when you read such a paper, you try to understand what it means, because of course, if you look in a dictionary and you ask, say, what is a fundamental constant, then it has to be constant, otherwise what it is. So I started to try to understand what are fundamental constants, and of course, they are important in all these debates about the multiverse, because people are using them to derive order of magnitudes, to make just to state this argument of fine tuning or coincidence. So it's important to know what are these constants, how do they enter our construction of physics. And then after a while, I wrote some papers and I had to do some popular science talks, and I chose the title, Are Constants Varying? And then I realized, okay, if you start like that, you have to go and try to define fundamental constants. So I went back to these things, and this is what I will try to tell you today, and what they teach us about physics and cosmology. And in my second talks, I will come back on these ideas that they may be varying and try to explain to you what kind of constraints we have and what we have to do in terms of pure physics in our observable universe to constrain this kind of thing. Okay, so the first thing, this is one of the only things I really learned at school is that when you don't know a word, you just go to the dictionary and look for it. So this is what I did. And so I went to constant. There are, of course, many definitions. The one we're saying is in physics, and we can read that it's the numerical value of some quantities that allow us to characterize a body. Quantities whose value is fixed, like the mass and charge of the electron, the speed of light, and that play a central role in physical theories. Okay, so you read that, and then you think a little bit, and you ask yourself many questions. And the first kind of questions that you raise is how many constants? We have some quantities. How many constants do we have? We have given a list of fundamental constants. Are they all on the same footing? Can I compare the mass and charge of the electron to the speed of light, or are they fundamentally different? They play a central role in the physical theory. What is this role? What role do they play in this series? And can they vary? According to the dictionary, no. So the question is solved. So we have to do better than this. So I tried to ask myself, okay, what is a fundamental constant? And this is now what I will try to explain to you. And I will come back to the connection between fundamental constants and the laws of physics. And the most important connection to me is a relation between fundamental constants and general relativity. And of course, if you think about general relativity as a theory of gravity or falling object, you ask what is the connection between fundamental constants, which are pure numbers, and falling objects. And this is what I will try to explain to you. Then I will give you some examples of theories in which what you think are constants may be varying, and this is the link with high energy physics. And then I will go to some reflections about fine tuning and landscape, but just to give you some kind of thought which are kind of disconnected, but that may help in thinking about fundamental constant in a larger framework. So let us start by constant and physics. So if you want to know what is a fundamental constant, I think the best place to look is to look in a book of physics. So you take many books of physics, you know at the end of all these books you have like pages of fundamental constants, and then you realize that, well, these lists differ. If you take a book from the 19th century and a book from the 20th century, you don't have the same list of fundamental constants. So these fundamental constants, they tell something about physics, but they tell something more on the theories of physics. And so this is what I did, and then you realize that the list of constants depends on when and by who the book was written. So in the 19th century, you cannot find the Planck constant in a books of physics just because you don't have quantum mechanics. And then you have some older constant which has disappeared from the books. So basically, these constants, they tell you something about the theories of physics, the theory in which they are appearing. So what I will call a fundamental constant now is any parameter that is not determined by the theory that I'm working with. So I am at the moment in the history of science. I'm using some physical theory. They are in agreement with a different kind of experiments. I take them for accepted theories. And in these theories, I have numbers that I cannot explain. The only thing I can do is measure them. And this is what I will call the constants. And they have to be assumed constant for two reasons. The first is that in this theory, there is no way you can get an equation. There is nothing more fundamental in terms of which you can express these quantities. So they are there. You can just measure them. And if your theory is in agreement with experiments, it means that you can reproduce your experiments, which means that at the accuracy of these experiments on time scales, which are typically on many years or centuries, Well, the reproducibility of experiments tell you that they are not varying, because if they are varying, if you see that one of the quantities that you have to assume constant in this theory is varying, then you will have to explain these dynamics, which means that you will have to extend your theoretical framework. So for this experimental fact and theoretical fact, they have to be assumed constant. So basically, this list of numbers, it shows something not our knowledge of physics, but more about our ignorance of physics. These are these numbers which are there. We can just measure them, and we would like to know where they come from. So studying the fundamental constant is the way to study the limits of a physical theory. And this is, I think, a very important point, because when we are doing physics, we are discussing with laws, but also with domain of validity. We would like to know how under which conditions these theories are valid. And basically, this domain of validity is quantified by these fundamental constants. So today, how many constants should we consider? Do you have any ideas of how many fundamental constants we have to consider today when we are doing physics? Well, I guess just to answer the answer, to get the answer, first we need to agree on what theoretical framework is the good framework to describe all physical phenomena today. So it's clearly not string theory. So what I would say is that there is no reason to doubt general relativity from an experimental point of view. We know it's not complete because we have many arguments that have been discussed before. But as far as experiments and agreement between theory and experiment is concerned, GR is fine. And I'm very glad. You know, I started my career, my PhD was in general relativity. So as long as it's fine, I'm just completely happy. Then you need to describe non-gravitational interactions and the matter sector. And usually you describe it by the standard model of particle physics. We have discovered the Higgs field today. And we know that all the particles that we are looking for are there. And basically there is no hint of any physics beyond the standard model. We are looking for it, like supersymmetry and many other candidates, but we don't have any. The only clue we have that we have to go from an experimental point of view beyond this standard model of particle physics is dark matter, and the fact that we have seen that neutrinos have masses. So there are these two experimental facts that tell us that we need an extension to these things, but we don't know what is this extension. So I will stick to this theoretical framework, general relativity plus the standard model of particle physics. And if I count if I try to make a list of the constants which appear in this theory, well, I have the Newton constant. I have all the Yukawa couplings for quark and lepsons in order to get the mass of the particles. I need to have the mass and the vacuum expectation value of the Higgs boson. And then I need to have some matrix which describe the property of the quark. So this is a CKM matrix. It has 4 parameters. And then I have coupling constant from the 3 non-gravitational interaction. And I have a cutoff, which I need to have. And then I have the speed of light, the Planck constant. And as has been discussed before, cosmology tells us that we need to have a cosmological constant. So it makes a list of 22 parameters and 22 constants. And I will explain what I call the parameters later on. And all these constants today, they can be measured. I have not updated my slide, unfortunately, but now we know about these two numbers because we have detected, we know what is the mass of the Higgs. So for all these numbers which you want to do physics, you measure them with a given accuracy. So this is very good because it tells us that we don't know what are these numbers and we are able to measure them. And it's very important for a constant, when you have a constant in a theory, that you are able, in principle and in practice, to measure it. If you are not able to measure it, then your theory will not be complete, will not be predictive. Okay, this number will change with time. It has been discussed at length. You can take the book by John Barrow. It explains all the way you can change. A constant can appear, disappear, because this number is time dependent. It's time dependent because our knowledge of physics is time dependent. We are constantly understanding new physics and the framework with which we are working. So it can increase. I said before that we know today that neutrinos have mass. So if we want to include a mass for the neutrinos, we know that we need at least 7 more new parameters in our model of particle physics. And this is the minimal number we have to add. If you go to supersymmetry, it could be more than 100 parameters, extra parameters. So this number can increase, this number can decrease. And one reason could be unification. We know that the coupling constant change with energy, and in the many models of physics, you have ground unification. If the 3 interactions are unified at high energy, it means that to specify these 3 numbers at low energy, you just need 2 things. You need the value of the unified coupling constant and the energy of the unification. So you reduce from 3 numbers to 2 numbers. So these are 2 examples in which the number of constant can increase or decrease. So it has to change. Okay, so now let me talk about these fundamental parameters and these fundamental constants. So the question is, if I take this list of constants, are they the same, to be considered on the same footing in the ways they play a role in the laws of physics? And to answer this question, I will go back to an old paper by Jean-Marc Lévy-Leblanc from the 70s. He was trying to make a list of the universality of constant, and for that he defined 3 classes. So the first class is that he called A, characterize a constant which are constant which characterize a given physical system. So it could be the mass of the electron. The mass of the electron characterize a system that you call the electron. Then you have constant from the class B. They characterize a class of phenomena, and this could be the charge of the electron. The charge of the electron is, of course, the charge of the particle you call the electron, but it's also just the unit charge. So it has something more universal than just being the charge of one given particles. And then you have constants which are called universal constants, which appear in all laws of nature, and we know just 3 of them, which are the speed of light, the Planck constant, and the gravitational constant. But again, this classification depends on time. If you just think about the speed of light, when it was introduced by Roemer, it was just characterizing light. Then after Maxwell discovered electromagnetism, because we didn't, unfortunately for us, it was understood that the speed of light was the speed of propagation of any electromagnetic wave in vacuum. So it was like characterizing all electromagnetism phenomena. And then it became a universal constant, and maybe you know even that it's more than a universal constant, because now the value of the speed of light has been fixed by law since 1983, and I will come back on this evolution. What is important with these 3 constants is that they really play a role in the way physics has evolved, because they play an important role which Lévy-Leblanc called the role of concept synthesizers. Actually, what happened when you develop new theories, you take different fields of physics, you develop different concepts, and you extend the domain of validity of these theories, and then you come with some incompatibilities. And to resolve these incompatibilities, you have to introduce new concepts. And actually, this is what these fundamental constants have done. For instance, you had the concept of space and time. You have with special relativity to come to the concept of space-time. And to do that, you need the speed of light, because you have to compare space and time, and there are some things that you cannot compare unless you have a fundamental constant to bridge between the 2 different concepts. In quantum mechanics, before quantum mechanics, you have the notion of particles and waves. You want to compare masses, energy to wavelengths and frequency. And to do that, you need the Planck constant. So basically, this is because you have the Planck constant that you can go from these 2 separate concepts, particle and waves, to the concept of wave functions. So that's a very important role. And then you can take all what you know from physics, and this is what I did with a friend of mine. So we took like the 3 fundamental constants, Planck, speed of light, and gravitational constants, and then we take the different theories of physics. So for instance, the incompatibility between thermodynamic and electromagnetism is resolved by the introduction, the understanding that we have quantum mechanics, and the link here is related by the introduction of a new constant, which is the Planck constant, and so on and so on. So this is A, B, and C. So you see that each time you have this kind of conceptual jump in which 2 theories like electromagnetism and Galilean invariance, sorry, it's in French, I'm sorry. You understand everything, French is so easy. So the incompatibility between electromagnetism and Galilean invariance give you special relativity, and it is associated with the change of status of the speed of light. Okay, because now the speed of light we characterize causality. Whatever the physical theory you are using, you want to write down a theory which has this kind of invariance. So you can play this game, and basically by the change of status of this fundamental constant, these 3 fundamental constants, you can just write down, try to see how the different domains of physics which were independent before just have tried to get a larger and larger domain of validity and had to merge together. And of course we are discussing this incompatibility between quantum field theory and general relativity, the problem of 0-point energy, and maybe, so there is a question mark here that we don't see, maybe the cosmological constant is the key to this last unification. And this is what has been discussed by Nima before. So this is the first thing. So we see that these 3 constants, they are very important. They really enter all laws of physics. So now we want to discuss whether some constants may change, and you have to ask the question of, well, they have a value, but if I take the value of g, it is given in the kilogram, meter, and second, so it depends on some units. So you have to be very careful about what you mean by unit of system and system of units. And actually, these things came back to me when I was reading this Asterix cosmic with my son some years ago. And there is this, I think, like a beautiful piece of paleo, how do you call that? Paleometrology in some sense. So this is, I will translate that. So we are talking, so this is Asterix at the Olympics. So this is the stadium, and we are told that the field has a length of 192 meters, 27, and that it corresponds to 60 times the length of the foot of Heracles, because everything was given in foot before. And you know, like most of these units, they were anthropomorphic. When you say the foot, you have to say, well, whose foot is that? And then, of course, they reverse the things, because you know what is the length of a meter today. You go and measure, and you get to the conclusion that the semi-god has a shoe size of 46. So that's, you can reconstruct what is the units in this case. So all these units, they depend on some reference person, and more important, they were varying from region to regions, and it was like at the origin of a huge confusion and of names, and if you were trading, then there were problems from one region to different regions. There is I think in the history of science, one critical, it's not because I'm French, but I think it was like one of the most important evolution in the relation between science and society was what happened during the French Revolution concerning the system of units. So people were kind of bothered by this kind of confusion, and when we were trying to construct the new republic, they were saying we want to have one length, one weight. And this was, some politicians heard that, and they came to the National Assembly, and in particular, Charles Maurice de Talleyrand, it's a very famous politician. He went through all kind of, he worked for Napoleon, he worked during the Terror, he was all the time, he survived all regimes, so he's a very smart guy. And on the 26th March 1791, he went in front of the Assembly with a list of all the units that were used in France. And he says, we cannot go on like that. We have to define a unit length and a unit mass. And he asked the French Academy to make a study, and they proposed 3 definitions for the unit length, for what we will call the meter later on. So the 3 proposals were first the length of a pendulum that is oscillating at the rate of 1 second. Then it was a fraction of the size of the equator, and then a fraction of the size of a meridian. And people had to choose. First, they knew that the length of a pendulum depends from the place where the pendulum is, because we had this trip in Peru and in Laponia, and they knew that this pendulum was not the same. Some people were going, so we just have to define that as the length of a pendulum that will be oscillating at the Observatoire de Paris, which is for some people very good. But then you have the ideas from the revolution that you have to work not for your own country, but for all people and for all time. So if you want to work for all people and all time, you need to get a definition that can be used by anyone on the planet, wherever he or she is living. So you just reject this possibility. You reject also the possibility that you take the fraction of the equator, because, well, there are very few countries on the equator, so if you have to measure the length of the equator, it's very difficult. But if you take a meridian, there is a piece of meridian going through any country, so anyone can go and measure the length, part of the length of a meridian. And this is actually what was done in France during 7 years by 2, like genius for me, Méchain and Delambre. You know, they went and measured the meridian from between Dunkirk and Barcelona. It took 7 years. It was the terror, the war, and it was like marvelous. You have to read the book by Ken Adler on this thing. It's a marvelous story, and it shows one value of science is that if you believe in progress and whatever is happening in politics, you're just going through, and because you are not working for yourself, you're working for the whole society. And I remember reading that when I was a kid, and it's really, I think, something which you have to keep in mind when we do science. So at the end, they managed to measure this part of the meridian and come from this length of unit. This is the meter. If you come to Paris, you go in front of the Senate, and then you have one of these meters. So in 1797, you had, I think it was 16 of them. Yes, 16 of them all over Paris. And any merchant can come and just, see that what his stick that is supposed to be a meter has this length. And then that was the definition of the meter, the creation of the international system of units that everyone, actually almost everyone, adopted. For the funny story, France was one of the first countries to define and to push for this system. But when Napoleon came back, he didn't want to use this system. He came back to Napoleonian units. Don't ask me why. So it has been developed, and this is what we use today when we're doing physics. And this system is based on some units. We have 7 base units, which are the Kelvin, the ampere, the mole, the candela for luminous flux, the kilogram, the meter, and the second. And this is the accuracy with which we can realize these units in the laboratory. So each of these system of units is a physical system. It has a definition, it's a physical system, and if you want to make any measurements, what you have to do in your laboratory is first realize this system and compare a new system to this system. And from that, you can measure any fundamental constant with a given accuracy. Okay, so that's the way it's working. So we have a physical system, we want to realize this physical system. Then when physicists thought about that, they realized that this is not perfect. In particular, Maxwell pointed out that, well, we are using the size of the Earth to define the meter, but we know that the size of the Earth may change with time on geological time scale because the Earth may cool down or there may be meteorites coming on the Earth, so the size may change. At the time, he was working on what he called atoms, molecules that we call atoms today. And he knew that these atoms, they were associated with some vibration and masses that were characteristic of these elements. So he proposed that, well, instead of using the Earth, we can use this fundamental object, which we call molecules. I mean, he was calling molecules. And just a couple of years later, after he gave this conference, George Johnston Stoney, who is an Irish researcher, understood that you can use, instead of this object, you can use a fundamental constant to derive a system of units. So he used the mass of the electron, the charge of the electron, the gravitational constant, and the speed of light to define a system of units. And this system was rediscovered by Planck. After he introduced the Planck constant, he realized that you can use the Planck constant, the speed of light, and the gravitational constant to define a unit mass, a unit time, and a unit length. And this is what we call Planck units. And usually, so in this unit, the numerical value of the gravitational constant is 1, and the numerical value of the speed of light is 1. It's 1 Planck length by Planck time. This is what has to be. It's not 1, it's not an absolute number, but in this system of units, it's 1. So what is important to remember here is that this is the evolution. So you start from some physical object, then you learn something about the theories of physics, and you decide that maybe the best way to define units is to use the laws of physics themselves. And actually, what is interesting is for many years, people have said, oh, this is a very nice definition, but we can never do that in the laboratory because it will mean that we will never be able to reach the accuracy needed to make high precision metrology. And the development of recent metrology actually now shows that this is where we are going to. I mean, this is something which is still in debate today, but the idea is to change the definition of the international system of units in such a way that the charge of the electron would be exact, the Avogadro number would be exact, the Planck constant would be exact, the speed of light would be exact, and the Boltzmann constant would be exact, which means that the only physical system you would get would be a clock. You will have a clock, so this is a frequency hyperfine structure transition in cesium that will define the second. And from this, because you have fixed the exact value of this fundamental constant, then you will derive the value, this new unit. So it's a completely shift in the way of thinking physics, because now the fundamental constant have an exact value, and the accuracy is on the realization of the system of units. So it's a different way of thinking about physics. And what I like here is that the only device you need is a clock. So if you have ever done general relativity, this is what you dream of, just having a clock, because this is the only thing that you can be sure of is the clock you are traveling with, even not the clock of your neighbor, but your own clock. So it means that anyone can just, with a cesium clock, just define the whole system of units. So this is the way the new system of units is working. So now, I mean, the summary of that is that you take all the constants you know in your laws of physics, you pick 3 of them, you can choose the one you want. From that, you will define what I will call 3 fundamental units, and we can choose them to be the Planck units, for instance. And then in these units, all of the numbers, they are dimensionless numbers. And the question is, where are these dimensionless numbers come from? Because this dimensionless number, now, you can ask whether they change with time. It has a meaning because you are sure that it doesn't depend on the way you measure them. And can you predict the value of these dimensionless numbers? So they are unexplained dimensionless numbers that tell you everything about the standard proportions in the world you are living in. So you would like to understand them. So this is the first key thing about fundamental constant is that you can separate and 3 of them, and then you just have dimensionless numbers. Okay, so this is basically what I say. So So then the next point is the connection between fundamental constant and general relativity, which to my mind is one of the most important. Sorry again, I have one slide in French, but and it's like it's an insult I'm making to you because there is a sentence by Newton, so it's just okay. So what is important is about the equivalence principle. So the first thing about the equivalence principle is what Galileo realized, is that if you are in vacuum and you take 2 different objects and you let them fall, all bodies will fall with the same speed. This is an experimental fact from Galileo. And then it was formalized by Newton. This is translated by Émilie du Châtelet. And basically, he's saying that the force is proportional to the quantity of matter of a body, and it differs from what we call inertia, the inertia of matter, but only by the way we have to conceive it, which means inertial mass is the same as gravitational mass. So if I just put formula there, we have that the force is the inertial mass times the acceleration, while the weight is the gravitational mass times the acceleration of gravity. So you have a special relation between acceleration and acceleration of gravity, and you have this ratio, which is the ratio of the gravitational mass to the inertial mass. And Galileo is correct, then if you take 2 bodies, 1 and 2, and you compare the relative acceleration, this has to be 0. So you can introduce this eta parameter, which is the difference of acceleration divided by the mean acceleration, and see how close to 0 this is. You can make experiments about that. And then the simplest thing is to take a pendulum, like a swing. It depends on the length of the swing and on the acceleration of gravity. So basically, you have the frequency of the pulsation of the oscillation. So now if you have a violation of this universality of free fall, the pulsation is not omega naught, which is this universal thing, which doesn't depend on the chemical composition of your swing, but it is corrected by this ratio m gravitational divided by m inertial. So if you take 2 swings and you compare them, you can see whether there is a small dephasing, and if there is one, you can put a bound on the value of this eta parameter. And this is basically what was done by Newton, and then was improved by Bessel. So the shift here to get 2 orders more of magnitude was just to make a mathematical modelization of the friction with air, which is a very important effect in the accuracy. And you see, at the time of Bessel, you were getting to 10 to the minus 5. And then you have to change the technology. You go to torsion balance. And then you can improve that to a level of 10 to the minus 13 by looking at the orbit of the moon. And this is a very nice experiment where you know that we have been, some people have been on the moon, and they've put some mirror on the moon. We call that retroreflector. Here they are. And you have different stations on the Earth, and you can shoot at the moon with a laser beam. And you compute the time for the beam to come back. So you do triangulation so that you can measure the distance between the Earth and the moon at a centimeter level, and that it has been done during 30 years. So you can check that the Earth and the moon are falling exactly in the same way in the gravitational field of the sun. Okay? And we know that if the universality of free fall is violated, there should be a polarization of the orbit of the moon. This is called the Laplace effect. It has been rediscovered by Kenneth Nordtvedt in the relativistic framework. So but Laplace, explained to us that if the universality of free fall is not valid, we should see that on the orbit of the moon. And now we are checking that. So it's and this is the reason why we can constrain its validity at the level of 10 to the minus 13. In the laboratory, what we do is we use torsion balance. And again, by using this torsion balance with different kind of test bodies, you see that the typical value of the validity of the universality of free fall or equivalence principle is at the level of 10 to the minus 13 also in the laboratory. So it's kind of very important. So this is in Newtonian physics. Now if we shift to general relativity, this universality of free fall will kind of be generalized to a new concept, which is the Einstein equivalence principle. And the Einstein equivalence principle states 3 things: the universality of free fall, and the local Lorentz invariance and local position invariance. And basically, these principles, they tell you that if you do 2 experiments of physics, let's say spectroscopy experiments, in 2 different laboratories, in 2 different places in space-time, you should get the same results. And if you do the same experiment in two free-falling laboratories, so that the relative velocity is just uniform velocity, you should also get the same result. It's a generalization of the special relativistic invariance. And if you have this Einstein equivalence principle, then you can show that actually gravity will be the consequence of the geometry of a spacetime. So it's a very, very deep principle of physics. But of course, it's not it's a principle, it's not a basic principle, it's an empirical fact. So if we ever find a reason that there is a violation of one of these three statements, it will tell us that gravity is not described as general relativity, and we have to go beyond general relativity. From a technical point of view, once we have this equivalence principle, it tells you that the action describing the matter is reduced to the fact that all matter fields are universally coupled to this physical matrix. So it's very restricting the form, the functional form of the action of the matter fields. So what is interesting, I want to flash that because for me it's one of the most interesting developments in physics in the past years, is that we can take two clocks today, and you see the relative velocity of the two clocks, and you see this is what is predicted by special relativity here, and this is the measurement of the relative frequency of the two clocks. So you see that the Doppler effect here at the level of 10 to the minus 15, and here it's even more striking, is that you take two clocks and you lift one of the two clocks by 33 centimeters, and it has to imply that you will have a shift of the frequency by 3.4 times 10 to the minus 17, and this is exactly what you see here. So we just test at this level of 10 to the minus 17 the consequence of this universal coupling, which is due to the gravitational redshift. This is what is often called the Einstein effect. So for me, it's really something which is very impressive. Just on your laboratory, at this level, you see that, well, this universal coupling has to be there. So it's somehow impressive. So now you have this new field which describes the metric of spacetime, and of course you need to have a dynamics for this field, and the standard dynamics of general relativity is to assume that you have the Einstein-Hilbert action. And here I put the G star instead of the G. It's another metric, which I will call the gravitational metric. And so you can construct a whole class of theories which satisfy the equivalence principle, but with two different metrics. What general relativity tells you is that these two metrics, the physical metrics and the gravitational metric, have to agree. And this means that the equivalence principle has to hold in the strong in the strong form, which means that if you take a body which has a non-negligible gravitational binding energy, two bodies with non-negligible gravitational energy, they will fall in the same way in their own gravitational wave. So basically, the fact that they have to agree tell you something about the nonlinear structure of general relativity. And well, it is assumed that, well, it is a conjecture because it's not proven, that general relativity is the only theory which satisfies the equivalence principle in the strong form. So this form of the action can be also tested, and we have a lot of tests in the solar system. I will not describe all this, but basically you are using the standard observation like light deflection, the shift of the perihelion of Mercury, the Nordtvedt effect or Laplace Nordtvedt effect, which is a polarization of the moon, and Shapiro time delay. And basically you have two parameters which characterize a whole class of theories of gravity, and general relativity is this small point here, and these are different experimental constraints. And basically what you get is that you have to be very close to general relativity at, let's say, 10 to the minus 3, 10 to the minus 4 level. So it's impressive. We have very few possibility to depart from general relativity today. So now what about constants? We know that in general relativity, any test particle will follow a geodesic. It's coming from actually this equivalence principle. And that this geodesic will not depend on the mass and the chemical composition of the body. So that's something we know. So now imagine that some constant change in space and time. The first statement is that local position invariance will be violated. Imagine that the Fein-Strassler constant is different here and on the moon. I do two spectroscopy experiments, I would get two different results. So it will be violated. So we know that the Einstein equivalence principle will be violated. What is more interesting is to realize that also the universality of free fall will be violated, and the reason is the following. So I just sketched the argument in a pure Newtonian way, but So the idea is that if you take a test body and you want to know what is its mass, you know that its mass is the mass of its constituent plus the binding energy. So it has to involve all the fundamental constants. You have the fine structure constant which enters through the electromagnetic binding energy. So it means that if any of the constants is varying in space-time and you have a body which is moving in space-time, its mass will change in space-time. So now you want to know what is its motion, and you can show that it's no more a geodesic motion, it has a force, and that this force will be proportional to the velocity and will depend on the change of range of this fundamental constant and how this mass depends on this given fundamental constant. But you see this dm over d alpha, it has to depend on the chemical composition of the body. The electromagnetic binding energy, for instance, depends on the charge number and the atomic number. So it means that instead of having a pure geodesic, you will have an anomalous acceleration which will depend on the chemical composition. So if fundamental constants are depending on space and time, then you expect to have a violation of the universality of free fall. So now it means that, well, if I test for fundamental constant, what I'm doing is actually I'm testing general relativity. I'm able to extend the domain of validity of general relativity because all the tests I presented before, they are done in the solar system. Now, if I want to make observation in other galaxies, maybe I can check whether the constant have the same value on other systems during, a few seconds after the Big Bang or in remote galaxies. And if I manage to show that they have the same value, then of course, I'm extending the domain of validity of general relativity, and this is very important because, as we know, there is a need to test general relativity on astrophysical scales because all these dark matter and dark energy components today, they come from the fact that we assume the validity of general relativity on these scales, on domains which are above the domain of validity of what is tested in the solar system. Okay, so this is very important. Whatever we do, we will learn something. Either we extend the domain of validity or we will discover a new explanation for these dark components. When I write down, if I use a field theory and I have an action for my fields, so I will have all the fields and I will have all the constants, what I will do is I will vary with respect to the fields and the constant will remain constant. So that will give me a set of equations for all dynamical fields that I will need to solve. I want to point that the action is not just a list of symbols because when you have a constant, for instance, you have to decide. If you take a potential and you assume that one of the parameters is a constant, you vary in a given way. If you say that it's a Lagrange multiplier, you vary in a different way. So you have to be very careful. It's just not what you have written in terms of symbols. You have to, there are a lot of things which are hidden behind the symbols. What is important now, if you want to have one of these constants become a dynamical field, you cannot just let it vary in the equations. You have to assume that it's varying, it's becoming a dynamical quantity in the action, and to rederive your action. So you will have one more equation, but also when you will vary with these quantities, there may be derivative of these quantities that will appear. So you won't get the same set of equations. So you have two consequences. The equation will be modified, and they will provide a new set of, a new equation for this new parameter. So actually, everything will be consistent together. The fact that it's varying, there is no inconsistency with conservation of energy or blah, blah, blah. So these kind of ideas have been used quite a lot. I just flash a couple of examples. This is what we call scalar tensor theory. So here in blue, this is general relativity. We have the metric, the Ricci scalar, and the coupling to the physical metric. But imagine that you introduce a scalar field with a dynamics and a potential, and you assume that matter is coupling to this, not to G mu, to the physical metric, but to this physical metric, which is not the gravitational metric, but with this conformal factor. Then this will be interpreted as a varying mass or varying gravitational constant theory. And if you take two masses, then there is a force, which is the exchange of a graviton, this is this term, and the exchange of a scalar, which is this alpha square, which is defined in this way. Which means that if you make a Cavendish experiment, well, you are not measuring this quantity G, you are measuring this quantity which depends on alpha, which is dynamical, which means that it can change from places to places. So this is the first example of theories in which you have a varying constant, which may be the gravitational constant. So now one of the key points here, it's a bit technical, but don't forget, take that as pictures, you don't care. Imagine that I want to have a varying fine structure constant. I may say, well, I'm coupling these quantities to the Faraday tensor. What is important here to remember is that if I take any atoms, for instance, the fact that I'm modifying just the electromagnetic sector doesn't mean that the mass are not varying, because most of the mass of the atom are coming from the electromagnetic binding energy. And if you put numbers in it, you will realize that the typical order of magnitude of the violation of the universality of free fall is 10 to the minus 9 times a number that will scale between 0.1 and 10 times the logarithmic derivative of this function, which means that it has to be smaller than 10 to the minus 13. Which means that this number has to be small. You have to be very close to the minimum. If you are not, then you will have huge violation of the universality of freefall. And this is a key problem when you will deal with theory with varying fundamental constant, is that if you are not sure that you are attracted fast enough toward general relativity, you will have huge violation in the solar system. So this is a point which is very interesting, because we will have constraints coming from cosmological scales and local scales. And by taking the two hands of these things, local scales and cosmological scales, we can kill a lot of models. Then, of course, you can talk about other theories like string theories, and in this series, you will realize that the value of any dimensionless constant is actually dynamical, because it depends, as Nima was pointed that out, on the geometry and volume of the extra dimension, on the dilaton, and all these things are dynamical quantities. And you see that there is a kind of evolution in what we are including in our physical model, because at Newton time, space-time is fixed and the constants are also fixed. With general relativity, space-time is becoming dynamical, and now with this high-energy theory, what we call constant today, they are actually dynamical quantities. The question is, if they are varying, how can we explain that they are so constant today? So this is a challenge for this theory to explain how the stability is constant. Okay, so you basically flip the problem. Okay, that I won't discuss right now. So the question now is, can we make such models? And I will probably discuss some of them tomorrow. I just want to say this is basically how all these things started during the last century, because the first argument was from Dirac in 1307, which was mostly a numerological arguments. And on the other hand, we have this development of Kaluza-Klein theory, which are multidimensional theories, and it was shown that you can have a varying gravitational constant. And I think the first actually theoretical understanding was by Jordan in the early 50s. We realized that it has to become a dynamical field. And what is interesting is that you have theoretical developments, but at the same time, people were coming with way to constrain and to test these ideas. And I will discuss all these things on tomorrow. So it's a very nice way to look at the development of theoretical physics and its interplay with experimental physics. Okay, so this is, I call that micro landscape. I don't know whether this is the correct name, but for some reason I will explain tomorrow. There is this idea to ask whether we can make models in which the fundamental constant just take different values in spatial patches. And so we came up with Keith Olive and Marco Peloso with this idea that, well, if you have a phase transition in some theories with a scalar field, the scalar field may take two different values on the size of a domain wall. And if some parameters are dependent on this field, well, there should be a discontinuity in this field. So these are words. I can show you the theory behind. This looks like that. It's just a picture, but just to tell you that we can construct the theory. So it has the Ricci scalar. It has some kinetics and potential for the scalar fields. And you see we have such a coupling here to the Faraday tensor. And the mass of all the fermions may be dependent on phi. So what is interesting is that the potential is tuned so that you have the possibility of a phase transition. So below a given energy, you will get domain walls and you will get patches of the universe with different values of this scalar field. So this is the way it looks like. So at the beginning, the potential is completely symmetric, but because of this coupling to matter here, it's not completely symmetric. So you have like two vacua, and the field can take the plus value or the minus value, and then the fine structure constant, the ratio of the different masses, they depend on the value of this fundamental constant. So you will get patches, and in each patches, because these are high mass scalar field, the field will be strictly constant. You won't see the time evolution. You just have different patches with different value of the fundamental constants. And of course, it has these patches, they have a typical correlation length which depend on the energy scale of your theory. And then you have two possibilities. Either I say that, well, these patches, they are small compared to the size of the observable universe, and in which case I will have a kind of, this is why I call that micro landscape, it's just that I will have patches with the fundamental constants with different values, and then I can make constraint on that because the microphysics of the phase transition is a priori accessible by some observations. We have observation of the universe on the past light cone, so imagine that, I mean, we are at the center of our observable universe. This is further in space, so at higher redshift. So I can interpret this variation, for instance, from here to here as a time variation. but it is actually a space variation because it's projected on the past light cone. But now if the energy scale is much smaller, then what I would get is that the correlation length is large compared to the Hubble radius, and then I would have, this is what I would call a landscape model, and I can realize it for a purely field theory. And it doesn't involve to have other universes. I just realize that in a universe for which the size is much larger than the Hubble radius. So this is a way to have a well-defined landscape, and this is, I think, an interesting idea, but you realize that in such a model, on the size of the observable universe, you will see no variation of the universe. Okay, so it's an interesting idea. So now we'll come back a little bit to some thoughts on these things about fine-tuning. And so, as I said before, we have all these numbers, and you see they are measured and with some given precisions. And one of the questions is, when do we say that two universes are different? And that maybe we can, I was interested by what you were saying, because we have these observers and we have this class of universality. If I take the fine structure constant, it is measured in the laboratory, and you see, well, we can measure it to this accuracy. But of course, 50 years ago or 20 years ago, we can measure it just at this accuracy. So we have improved the accuracy. Then, today, I would argue that in principle, I can distinguish two worlds in which the fine structure constant differ by the level of 10 to the minus 11. I can make two experiments, and I will be able to say, well, in this universe, this is 44, and the other universe, this is 67, for instance. But in practice, this precision, we don't care, because for most natural physical phenomena, like stars, atomic reactions, I don't need to use this high precision. Unfortunately, because if I just look at the prediction of stellar physics and I want to compute the typical abundance created by different kind of stars, I don't care about knowing the fine structure constant at the 10 to the minus 11 precision. Otherwise, I would not, I would have measured that by doing stellar physics or by doing Big Bang nucleosynthesis. What I can argue, and I will develop that tomorrow, is that it's enough to know that at the level of 10 to the minus 5 or 6. It's, for sure, like 10 to the minus 7 is far from anything that can be detected. So it means that today in the laboratory, we can have more precision than what is needed to have different kind of precision for the physical phenomena. So one of the questions I'm asking myself is, when should we say that two words actually are identical? Because if I take these two words with 24 here or 67, I would guess like all the stars will be exactly the same. All the abundance will be exactly the same. There is no way you can, because of all this fluctuation in the chemical composition and environmental effects, that you can see the fact that these two words are different. So, of course, if this is the fact that I can measure these numbers, then the problem comes that it will be dependent on the existence of these observers and the level of technological developments. So how do we take that into account? I don't know. It's just something I wanted to stress, because usually we're discussing about this fundamental constant, and I would argue that as far as natural fundamental processes are at work, I don't need a precision which is larger than 10 to the minus 5. And that's enough. And fortunately, because we have been doing physics and we understand that stars are working, and before we were able to measure these numbers at this accuracy. Then there is this relation with the entropic domain. So we had all this discussion about having an entropic domain. So we are using, let's say, the fine structure constant, the mass of the particle, like the quarks, and we say, okay, if they vary by more than blah, 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 then there will be a catastrophe. But you have to remember that if I make these constant dynamical quantities, it means that there is some kind of higher energy theories for which I have to populate these things, and each of these points, it will correspond to a low energy physical theory. So the question is, what is the relation between these two things? I have a mapping here, which I don't know, because usually, in general, I don't know anything about this theory. And the question about, I think about the fine-tuning is the following. Of course, we have the size of the entropic domain. We have the precision of what we can measure, which is inside this entropic domain by construction. It cannot be anywhere else. And then we have the way this high energy domain is populated. And the question is, how is it populated in this, how do you call that in English? Yeah, the inverse mapping. So this ensemble here maps to the entropic domain, and we have no clue of the side and the density of physical theory which lie into the side. So the fact that, of course, I think one of the things which we do not discuss in this entropic argument, because we don't know this theory, is whether it's populated enough that we resolve the fine-tuning. So Nima gave an example with this 100 scalar fields, and with this he was able, because of the choice of this 100 scalar field, to get enough splitting so that you densely populate this domain. But because we don't know this domain, and because we don't know anything the way it's populated, it's not even clear that we solved the fine-tuning problem. I think it's very important to keep that in mind. And then here you see I've put constant and initial conditions, because if you just come back to the simplest version with these 6 numbers, the Martin-Rees stuff, you have 2 numbers which characterize physical parameters, and they are related to the fine-structure constant, the strong interaction and gravitational interactions. And you have other parameters which are cosmological parameters. They are a completely different set of parameters. This one have parameters of fundamental theories. This one have parameters which enter some solution of the equation of these fundamental theories. I mean, if the universe does not have the Copernican principle, if initial conditions are different, then I cannot even define these quantities. So I interpret my data, I measure some cosmological parameter by making some assumptions on the cosmological solutions of this theory. So they do not have to be considered in the same way. And then the problem with the cosmological constant is this coincidence between the age of the universe today, the typical time scale associated with the cosmological constant, and the time to form galaxies. So it means that inside this solution, you want to say something about the fact that you are lying somewhere in the history of this universe, and you see this is characterized by a given constant, which is the Planck constant. So I would say that we probably need to distinguish a little bit the different constant which enters in the entropic arguments. I will call pi the values of fundamental constants, so the one which enter the microphysics. So they are inside the Lagrangian of the microphysics. Then I have this cosmological constant which include initial conditions, and they are the properties of a given cosmological solutions. And then I have what I will call localization parameters, which tell you at what time you are making your observation. And actually what I would like to propose is that we have something like that. We have like parameter for the theory, so basically the things coming from the Lagrangian, the cosmological solution, and then we are not sure even that we are using the correct cosmological solutions. And then we have this kind of bundle, and we have this parameter which tell you actually where you lie today in this given. So this is a given universe, a given physics, and a given solution of these physical equations. So, and what you would like to know is, well, what is the distribution of these quantities given the fact that you observe the universe from there? Okay, so if I understood correctly, this is what we really need to compute. And for me, it's not clear because there are kind of different layers of assumptions. And I was starting by doing theoretical physics, and I just make assumption of the solution of this series, and then I have to dig into the dynamic of each of the fibers. So it seems to be very intricate to actually know exactly what we are concluding from these entropic arguments. And this is basically where I want to stop, because I think what I wanted to stress is that fundamental constants, they teach a lot about the history of the construction of physics and the domain of validity of our theory. From a pedagogical point of view, it's very important to look at that. I think it should be in any course lecture in physics, which sometimes we don't. We're just doing mathematics. Then, as I said, we had 23 fundamental constants. If we go to argument, to entropic argument with 6 numbers, it seems that we are like throwing away a lot of information. It's like, so what is the minimal information concerning this constant that is important to draw conclusions? It's like if we had like the genotype with all this information at a like very, very high accuracy, and we just need some number with a given accuracy. It would be like some kind of coarse grain information that is required. What is actually the minimal information that is needed to describe all phenomena in our universe? And we know nothing about the distribution of this fundamental, the probability distribution of this fundamental constant. And I can construct many models if they come from a given scalar field with different kind of initial probability distribution function. So it's also something which is very unknown. And also, in all these models where they arise from a higher dimensional theory, the variation of the different constants are correlated. So you cannot just say that I'm moving one constant, but you have to move all constants together. And also you have to remember that in these things, what you are doing is a purely local analysis. You know what is the physics with the value today, and you make small variation. You don't know whether there are islands somewhere else in this space where there may be some variable physics. There is one example that has been proposed a couple of years ago where some people actually try to ask the question whether you can have a viable universe without the weak interaction, and they managed to construct one solution. So it's like no weak interaction. It's something which is completely different from what we know today. And then we're drawing conclusion from small variation around our own universe. And I think it's finished. And then I don't talk about the structures of physics, but okay, so thank you.